These are notes for section 8.6, which is on both the ratio test and the root test. First thing we're going to do is take a look at this series. The sum as n starts at 0 and goes to infinity of 6 to the n over n factorial. And we're going to briefly talk through all the things we've done so far. So the first thing we might check is check to see if the limit as n goes to infinity of the sequence 6 to the n over n factorial. And if it's anything but 0, we know that this series diverges. We can't really use the L'Hopital's rule because we don't know how to take the derivative of n factorial. But if we consider what's happening in the sequence, 6 to the n, which means the top I'm multiplying by 6 over and over and over again, times 6, times 6, times 6, times 6. And the bottom from one term to the next, it's going to be times 1, and then times 2, times 3, times 4, times 5, times 6, times 7, times 8, times 9, times 10. So notice that the bottom, as we get really far away from 0, the bottom is growing much faster than the top, which means that this is going to go to 0. Another way that you could check the sequence is if I plug in a bigger number like 17, 6 to the 17th divided by 17 factorial is indeed pretty close to 0. 6 to the 20th divided by 20 factorial should even be closer to 0. 0.002. Notice this is getting infinitely close to 0. So that doesn't tell us if it converges or diverges. It just doesn't automatically tell us that it diverges. So we can't use the nth term test. Notice this is not a geometric series. It's not telescoping. It's not alternating, so we can't use any of that. And then the other one that we've done is either the limit or the direct comparison test. And we don't really have anything to directly compare this to. We could try to come up with something, but it's not necessarily going to be easy to come up with something that when we take the limit as n approaches infinity of dividing the two things, that stuff cancels out. So based on what we've done so far, we cannot tell if this converges or diverges. So that's going to kind of lead us into the first of the two tests we're talking about today, which is the ratio test. The way the ratio test works is we are going to take the sequence and we are going to take the next term divided by the previous term and evaluate the limit as n goes to infinity. If that gives me something less than 1, then we know that the sequence converges absolutely. Whether it has an alternating part or not, it will converge. If it gives us something greater than 1, then the series diverges. And if that gives us equal to 1, that means that the ratio test is inconclusive. There's going to have to be some other way that you do it. The ratio test works great for terms that, or sequences that have factorials in them. Anytime you see a sequence or series that has factorials and we're trying to decide if it converges or diverges, we will be using the ratio test. So again, we're going to take the sequence of a sub n plus 1, divide by a sub n, evaluate the limit as n goes to infinity. If that gives us something less than 1, converges, greater than 1, diverges, equal to 1 is a bummer because you're going to have to consider some other way to do it. So example 1 asks us to use the ratio test to determine the convergence or divergence of that series we just looked at. So the ratio test is the limit as n approaches infinity of a sub n plus 1. So I'm going to replace the n's with n plus 1. Divided by a sub n. We're dividing by this fraction. That's the same as multiplying by its reciprocal. Absolute value we don't necessarily need to worry about here because we don't have an alternating part. If you do have an alternating part, that's just going to get rid of the alternating part. And then we need to clean this up. We want things to cancel out. 6 to the n plus 1 and 6 to the n, we should be able to simplify those. 6 to the n plus 1, I can write as 6 to the n times 6 to the first. And we did that so that this 6 to the n cancels with that 6 to the n. N plus 1 factorial, we can write as n plus 1 times n factorial. And now these n factorials cancel. As n approaches infinity, I have 6 divided by an infinitely big number, which goes to 0. 0, I am pretty sure, is less than 1. Therefore, this converges. Example 2, use the ratio test to determine the convergence or divergence of this series. Notice we've got a polynomial part, which we usually use the limit comparison test for. We also have a geometric part. We are doing the limit as n goes to infinity of a sub n plus 1. So replace all the n's with n plus 1. This would be 4 to the n plus 3. Divided by a sub n, which is this. Dividing by that fraction, we're going to multiply by its reciprocal. There's some absolute values on there. Again, we want some things to cancel out here. 6 to the n plus 1, again, we're going to write as 6 to the n times 6 to the first. That way, the 6 to the n's cancel. A couple different ways you could take care of the 4s. You could, because this is 4 to the n plus 2, we want this to be 4 to the n plus 2 times 4 to the, when I add the exponents, I should get n plus 3. Make that 4 to the first and then cancel these out. You could also split them both up the same way we did the 6. 4 to the n times 4 to the third, 4 to the n times 4 to the second. Either way will work. And I've still got this n plus 1 squared. So those canceled, those canceled. Right now I've got 4 times n plus 1 squared over 6n squared as n goes to infinity. If we were to expand this, the highest power of n on the top would be 2, and the highest power of n on the bottom is 2. So we divide the leading coefficients. This would be 4n squared, 6n squared, 2/3, which is less than 1, converges. Example 3, again, is asking us to use the ratio test to determine the convergence or divergence. Limit as n goes to infinity of -1 to the n plus 1 times square root of n plus 1 all over n plus 1 plus 1. Divided by this, multiplied by the reciprocal. This part here actually doesn't matter much, but if you did want to simplify it, it would look like this. So we could split that up the same way. and my -1 to the n's cancel. If we were thinking about the highest power of n, on the top here I've got square root of n, and if I distribute here I've got times n to the first. So the highest power of n on the top is n to the 3/2, and on the bottom I have square root of n times n to the first. That is also n to the 3/2. So if I divide the leading coefficients, I get -1 on the top divided by +1, which is -1. Absolute values mean this doesn't matter. Notice in this case I get 1. Anytime you only have n to an exponent on the top and the bottom, the ratio test, that's when it's going to be spitting out 1 like that. The ratio test is inconclusive. It told us to use the ratio test, so that's all we would necessarily need to state. Hopefully we recognize that we could use the limit comparison test. The n on the top is square root of n, on the bottom is n. So 1 over root n diverges. If you evaluate the limit as n goes to infinity, you will find that they do the same thing. So without the alternating part, it diverges. Remember, if we're comparing it to anything 1 divided by any p series that's bigger than 0, the alternating part will converge. So this converges because it's alternating, but it is a conditional convergence. It diverges without the alternating part. So that is the ratio test. I would always, anytime you see a factorial in it, automatically jump into the ratio test. If you don't see a factorial, you'll want to start to consider some other stuff. Like on this one here, this is very similar to ones we've already looked at. One like this, it has both geometric and polynomial in there. That'd be another good time to use the ratio test. But I'd kind of start, if it's not a factorial, start by thinking about some other things. If it doesn't look like any that were in the previous unit, then the ratio test can be a good option in that case as well. If you're not sure, go ahead and use the ratio test. If it spits out 1, there's another way to do it. I want you to pause the video. I want you to try these two. Check to see if each of these converge or diverge. Once you think you have it, I'll show you the work. So on number 1 here, if I replace all the n's with n+1, divide by the sequence, so multiply by its reciprocal, we get here. We want things to cancel out. n+1 factorial, we're going to write as n+1 times n factorial. 7 to the n+3, I wrote as 7 to the n+2 times 7 to the first. Again, the reason I do that is so that these two can cancel out. So these cancel, these cancel. As n approaches infinity, now my numerator is infinitely big, divided by 7. That is certainly greater than 1, therefore this diverges. For number 2, replace my n's with n+1. This one, because it's not really written as a fraction, I didn't multiply by the reciprocal, although you could. I just divided by this. Left this alone, change this to 2/3 to the n times 2/3 to the first. 2/3 to the n now cancels. Degree on the top is 2, degree on the bottom is 2, so we divide the leading coefficients, which is 2/3 divided by 1, 2/3, which is indeed less than 1, therefore this one converges. The other test, which is probably not quite as important, is the root test. The root test works kind of similar, but instead of dividing consecutive terms, instead of taking the ratio of consecutive terms, we are going to evaluate the limit as n approaches infinity of the nth root of a sub n. The nth root of a sub n. If that is less than 1, then it converges absolutely. If it's greater than 1, it diverges. And if it's equal to 1, then the root test is inconclusive. And we don't use this one nearly as often, kind of just a special circumstance when we use this one. First of all, we could use the root test here. Hopefully, we recognize that this is the same thing as 5, 6 to the n, which is geometric. So hopefully we're going to get converges here. If we use the root test on this, we would take the limit as n approaches infinity of the nth root of 5 to the n over 6 to the n. The nth root of 5 to the n is just 5. And the nth root of 6 to the n is 6, which is less than 1. We also get converges. The time that the root test is good is this one's not geometric because it has n to the n down here. Limit as n goes to infinity of 4 to the 5n over n to the n. We're taking the nth root. The nth root of 4 to the 5n could be written as 4 to the 5th to the n, and then the nth root would cancel with the n here, so that's 4 to the 5th. The nth root of n to the n, nth root of n here cancels, it's just n. As n goes to infinity, I have 4 to the 5th divided by an infinitely big number, which goes to 0. This one also converges. Page 602 in your book has a summary of all of the tests. So we've done lots of different tests. We are finished with testing for convergence or divergence. We'll still be working with series, but we have worked through all the different ways that we are going to test to see if a series converges or diverges. So if you're ever working on a problem and you kind of don't remember exactly all the different tests we've done, you can go back to page 602. It gives you all the conditions that need to be met for each of those tests. If you're having questions on anything, please reach out.